Okay, everybody, this is for AP Physics C. Have a slightly better setup than I had for Physics 11H here. Not much better, but I got a plan to build a little something when I get some free time this weekend, likely. So what I'm going to do for today is just kind of recap what we had done in class with simple harmonic motion, and then talk a little bit about that worksheet, which is going to be homework, just number 1 for homework for Monday. Okay, I gotta get some other resources to you here, make sure stuff's updated. It's all pretty crazy, right? Just trying to manage this stuff and home life. Gotta trade off with the wife back and forth, but she's got some work she has to do, and then we gotta entertain the kids. So here we go. Are you ready? All right, back to simple harmonic motion. I'm gonna kind of recap kind of what we did with that thing where we figured out the frequency of oscillation. All right, so I'm going to kind of look at the setup from the homework ditto. We have a mass on a spring. We displace it some distance here. Equilibrium position's right here. We displace it to some x max. On your worksheet, it's positive A. That's just a positive position. This is a one-dimensional oscillator. Over here, this we're going to call negative A. All right. And what we're going to do is find the acceleration of this object as it moves, right? There's 2 ways to do that. One way is to use Newton's second law, right? F net equals ma. And the other way is to use the equation of motion and take 2 derivatives of it. The equation of motion is the position and time function here. So for this one, we know that from experiment and just by observation that the position as a function of time is going to be the amplitude multiplied by the cos of its angular position, which is, theta, right? But that's also equal to the omega t. All right, so we call that omega t right there, cos omega t. So I'm going to go first through Newton's second law, then take a couple derivatives of this cos function, and then from there, we'll see how things fare and try to make some inferences about the frequency of oscillation. Okay, so first we figure out the forces acting on the mass, and if I draw a little force diagram here, to have the normal force, the force of gravity, and this one here, Hooke's law, negative kx, right, where x is the position vector. So therefore, when it's in our coordinate system, when it's to the right of the equilibrium position, the force is negative. When it's to the left of the equilibrium position, the force is positive. So negative kx equals ma. A equals negative k over m times our position. Cool. Now over here, so there's our position function, where this is our acceleration function. So now we take 2 derivatives over here. So first of all, velocity equals dx dt. So we get negative, so we got to do a little operation here. Negative omega a sine omega t. Cool. Then the acceleration, d squared x dt squared equals negative omega squared times a cos omega t. All right, so look, we took 2 derivatives of this. We ended up back to a constant times our original function. So why don't I write it like this? A equals negative omega squared times our original position function. So I found the acceleration in 2 different ways. They're both definitely the acceleration. This x here, position, could be represented by that position function there. And that's also this position function. So what we have here is, put them both together, we have negative k over m times the position equals negative omega squared times the position. Therefore, the angular frequency equals radical k over m. The x's cancel, negative signs cancel, take the square root of both sides, and from that we get all kinds of good stuff. Alright, we could find the frequency. Alright, so if this is in radians per second, right, we need to cancel out the omega, right? This is radians per second. We need to get it down for cycles per second. So omega over 2 pi would give me f. So f equals omega equals 2 pi times f. So that f equals omega. Divide out the radians. Alright. So the frequency of oscillation is 1 over 2 pi times radical k over m. And then you can figure out the period from there. 2 pi times radical m over k. Right? And that we then use that all over the place, right? We use that. Oh no, I went off the screen with that. Oh, that stinks. Oh well. I'm not gonna redo it. I'll just slide it up for you for this one. My bad. New setup. I'm gonna have to figure that out. Kind of funny. Yeah, sorry about that. Any questions, shoot me an email. Give this a watch. And we'll do that worksheet 1 for homework. Alright, love you guys. Talk to you later.